Hello, this is Edward Doolittle again with another Stat 100 lecture. This time we're doing 9.5, which is a large sample test of hypothesis for a binomial proportion. So here we're continuing with the hypothesis testing, and in this case we are looking at the discrete case, where we are counting rather than measuring. And so this is very similar to confidence intervals. We also did confidence intervals both for continuous case and discrete case. And in the discrete case, we are interested in the sample proportion of successes p. And this we don't know. This is p for the whole population. It's the proportion of successes versus the total population, or divided by the total population. And so we are going to try to infer information about p. What we do have is a sample proportion. So this is the population proportion. We have p hat, the estimator, which is the sample proportion. And we have n, which is the sample size. Okay, so we're going to use all the same techniques that we've been using. This is, again, a consequence of the central limit theorem and is directly analogous to the confidence interval framework that we studied in Chapter 8. We're just putting a different kind of framework on it, but it's really the same information. So there's nothing here that's really should be very new or very surprising. We are going to talk about one-tailed tests, two-tailed tests, and rejection regions, and so on and so on. So let's get to it. So we know that p hat, it has a for large n. P for large n. I'm going to just write this down. For large n, p hat is normally distributed with mean p and standard error this expression, which should be familiar to us from Chapter 8, Chapter 7. Okay, that's the central limit theorem. Now, we are going to try to make inferences about p in the hypothesis testing framework. So what we're going to do is to study alternative hypotheses. And those are the usual three variations. So in one alternative hypothesis, we're hypothesizing that p is different from some number, some specific value, p sub 0. This is always a number in problems that you do in practice, but for purposes of generality in making a statement or a method, I'm just going to write it as a symbol. The other two alternative hypotheses are where we're hypothesizing that the population is greater than some number, or that the population is less than some number, population proportion. This one, of course, we know is two-tailed, and these two are one-tailed. Okay, and one other thing I have, keep saying large sample. In the discrete case, it's a little different from the continuous case, and we know this as usual. N times p has to be greater than 5, and n times q is greater than 5. But because we are making a hypothesis here, we're going to use these values for p and q, because we don't know what p and q are, but we do know what we're hypothesizing they are. those are the numbers that we use for large samples. So this now becomes the large sample condition. All right. The null hypothesis in all cases is the usual null hypothesis, that P is equal to that number. Okay, so the last thing that we're going to make is an approximation. So the standard error is equal to PQ over N, and we can, of course, we don't know what P and Q are, so we are going to have to approximate them, and we do the usual. Well, in this case, we're not going to do the usual approximation by what we measured, but we have something better. We are going to approximate them by what we are hypothesizing them to be. So that square root sign goes down below the end there. So we are making a hypothesis that they have certain values, and that is what we are going to use as our P and Q for the purposes of calculating the standard error. So everywhere where we would use a P, we instead use the hypothesized value for P. And of course, there's a relationship, Q is equal to 1 minus P. This goes without saying, but I'm saying it just as a reminder. Yeah. P plus Q is always equal to 1. Okay, so this is the framework that we're using. We're making an assumption. We make the assumption of this null hypothesis, and what we're actually trying to do is to show that our assumption is wrong, or at least unsupported by the evidence, or improbable, so on. So we're making this assumption, but after we've made this assumption, then under that assumption, this is the correct value for SE under the assumption. This is the correct large sample condition under the assumption that we're making, and so on. So next comes the test statistic under that assumption of the null hypothesis. We calculate the test statistic is a z-score as usual in this chapter, and it is the usual form for a z-score. So it is p hat minus p sub 0 divided by the standard error. And p sub 0 again is the mean of our sampling distribution by assumption, because we're assuming that p is equal to p sub 0. Okay, and we can just fill in if we like to make one big formula with all the bells and whistles, but when you do this, you do have to remember the correct order of operations. Okay, so that is our z-score. And p hat, if, just in case you need a reminder, is equal to x over n. X is the number of successes in a sample, n is the sample size. P hat is the sample proportion of successes. Okay, after this, it is pretty much the same as always. This is the usual. We need to find the rejection region for the z-score, and it is the usual thing. Nothing here is any different from earlier in chapter 9. So we have two cases. We have two-tailed and we have one-tailed. So in the two-tailed, we have symmetric negative z sub alpha over 2, z sub alpha over 2. This is the acceptance region, where we accept the null hypothesis. And note again that it is the region that contains 0. And then these two regions off to the side are the rejection regions, where we reject the null hypothesis. Maybe I should just remove this, move it down here. There are two one-tailed cases. The one that appears in the textbook is where we have z sub alpha. Here is 0, so this here is accept. This here is reject. In this case, alpha over 2 is the probability, so the area of that tail, and by symmetry this is alpha over 2 is the area of the tail on the left. Here we just put all the alpha on one side, so we don't divide alpha by 2, we have alpha. And this is where the hypothesis, the alternative hypothesis is p is not equal to p sub 0. And here the alternative hypothesis is where p is greater than p sub 0. And then, of course, we have the third case where p is less than p sub 0. Okay, my drawing skills are very poor, you may have noticed. They're made worse by the tablet is kind of slippery compared to a sheet of paper, so I'm sorry, but really all that matters is the schematic of this, not the perfect artistry of it. In this case here, this is our accept. And this is reject. All right, so three different ways of drawing this important diagram. The exact values for z sub alpha over 2 and or z sub alpha are exactly as they were in previous sections. So there is nothing new here. And we can also do the p-value versions of these. So instead of rejection region, the pro way of doing this is to talk about p-values. And so in the two-tailed case, we have, here is our measured z, here is its mirrored image, and the p-value is the shaded total of these two shaded regions. And what we are looking for when we do the p-value method is to accept the null hypothesis when our p-value is bigger than alpha, and reject the null hypothesis when our p-value is smaller than alpha. So in this case, we have seen something that is improbable, which means that we reject our hypothesis. In this case, we see something that's probable, which means it doesn't say anything about our hypothesis. So accept is a strong word. What we may say instead of accept is fail to reject. But I'll go into that in a little while, a little more. Okay, so that is the p-value version of it. Let's just do one of the p-value versions for the one-tailed test, and the other one will be exactly symmetric. Z sub alpha, not Z sub alpha in this case, but just Z. So in the p-value version, we just draw Z. We don't draw in the critical values, and we find Z. Oops, I don't want that. Okay, I want to shade it like that, and there, the area p-value is area. And then the same always here. So it's nice to do things in terms of p-value because we have a very uniform way of interpreting the p-values, and this is across the board throughout all of statistics, we interpret the p-value using this method. So that's one nice thing about doing p-values, is that the interpretation of our p-value it never changes. The critical value method, the interpretation of our z-score depends on the critical value, but interpretation of a p-value is universal. It's always the same in any kind of problem, in any statistic. So it's maybe a little harder. There's an extra step of calculation for the p-value method, but it's kind of gives you more information. It's more universally applicable across different statistics throughout all of statistics. So it's something that, journals, if you ever end up writing a journal article or co-authoring a journal article, they will want to know p-values. It's an important thing. All right, so that is all there is. Oh yes, there is also the conclusion, and just as I did in the previous section, I'm going to say same idea as in previous parts of chapter 9. Okay, so that's it. We can do an example. I think I feel like just taking a nice example from the textbook, so we'll walk through this one. 9:14 in the textbook, and you have access to the online textbook now, so I can just refer you to page 383 of the fourth Canadian edition of the textbook. So here we go. Regardless of age, about 20% of Canadian adults participate in fitness activities at least twice a week. However, these fitness activities change as people get older, and occasionally participants become non-participants as they age. In a local survey of N equals 100 adults over 40 years old, a total of 15 people indicated that they participated in fitness activity at least twice a week. Do these data indicate that the participation rate for adults 40 years of age is over 40 years of age is significantly less than the 20% figure? So we have an alternative hypothesis. We are looking for the proportion of fitness buffs 40 years of age. We've done a random survey, random sample. We found, anyway, we'll write down what we found, but we're hypothesizing that the population as a whole has a significantly lower participation rate than the 20% that's been quoted. So we are calling this into question. And this is our job as researchers. We question things, and now we're going to use our statistics to try to answer our question. So we're making a hypothesis. The corresponding null hypothesis is that there is no difference between our population and the quoted statistic. Okay, so those are our two hypotheses. The textbook tends to write the null hypothesis first, but I don't like that. I like to think about the alternative hypothesis, because that's the whole reason we do research, is to investigate alternatives. Okay, now let's take a look at our sample. Our sample size was 100. The proportion in the sample was 15 people indicated that they participated in exercise and fitness activities, divided by 100 is the total sample size. This is X, this is N, and that is 15%, of course. All right, so that kind of sets us up. Now, next step, straightforward. We're going to calculate the Z statistic. The formula in this case is right, and note that we are using the hypothesized values for P and Q. So, the central limit theorem tells us that this should be P, and this should be P, and this should be Q. But we don't know P and Q, but we are making an assumption about P, which means that we can make the corresponding assumption about Q. And so these are the numbers that we use for P and Q in the central limit theorem. Okay, now I do this little calculation and I'm going to get negative 1.25. Okay, so this does not seem like a very out of bounds z-score. We see z-scores like this all the time. It's sort of common for us to see the z-score. So, right now I'm going to say probably that's not that uncommon. So I'm not going to be able to draw. I'm not going to be able to contradict my null hypothesis with this number. That's how I feel about it, though. We have to quantify things, and let's now think about that. So the question, let's go back to the question, how confident are we supposed to be in our answer? It says, do these data indicate that the participation rates for adults over 40 is significantly less than the 20% figure, blah, blah, blah. So notice that this problem does not have a confidence level quoted in it. So we have to figure out what the confidence level would be. But this isn't something that we normally figure out. It's something that is just taken from custom. Customarily, we use a confidence level of, this should not surprise you, of 95%. Right, so the problem doesn't say what the confidence level is or what the significance should be, so we are going to instead just take the customary value of 95%. And that's just something that has been developed by statisticians, scientists as an acceptable bound for publication. All right, so that means that alpha is 5%. Next, we have to note whether this is one-tailed or two-tailed. So let's go back to the original question. Let's look at the alternative hypothesis. Is this one-tailed or two-tailed? And you should recognize that it's one-tailed. Keyword in the problem is, do these data indicate that the participation rate is significantly less than? So that's a keyword you look for, less than, greater than, more than, smaller than. Those are all keywords for a one-tailed hypothesis test. So we note that carefully. Okay, so this is one-tailed. All right, so now the question is asking us to do the p-value method. So we're not going to, let's not fuss about the critical value. You can certainly do the problem that way, and I would recommend you give it a try. You should get the same answer that we get using the p-value method, but here I'm going to use the p-value method. So did I draw my picture? No, I didn't draw my picture. So let me draw my picture. I'm looking for significantly less than, so everything is on the left side here. Less than 0. I'm looking for a difference that's less than 0. And my noted calculated value of the z-score is negative 1.25. So this is the p-value. One-tailed, right? So we don't have to mirror everything on the right. And now I have to do a lookup on my z table front of the textbook. Negative 1.25. You should follow along with me, and you are going to get, you should get 0.0606. And that, let me check this here. Something doesn't jive here. Negative 1.25. Pardon me, I read that out loud incorrectly. Negative 1.25. I'm going to get 0.1056. So the p-value is positive, pardon me, 0.1056. It's this area. That is exactly from the Z table. Now we are going to compare the p-value. Is about 10%, 10.5%. That is greater than the alpha, which is 5%. And this tells us to accept the null hypothesis. All right. So what we should say, instead of accepting the null hypothesis, I prefer you to write it this way. So conclusion, there is insufficient evidence that percentage of adults over 40 to participate in fitness and all the qualifications, or twice a week or whatever, is less than 20%. But then we should quote the p-value. Okay, so journals will typically ask you to do that, put the p-value in brackets after you make a statement. So you're making a statement here, and the readers of the journal will want to know the probabilities involved in that statement. So when you use the p-value method, you should quote the p-value in your conclusion. This is how it will look when you put it into a journal article. All right, so that is it. It's all the same, pretty much. I mean, you have to pay attention to one-tailed versus two-tailed. Is it on the left or is it on the right? But other than that, these problems are all the same. So you should go ahead now and try a bunch of these problems. I have also given some extra problems from the textbook. I've chosen some fourth edition, not chapter 4, but chapter 9, fourth edition problems for you to try that are appropriate for us. And all the solutions are written out in long form in the Student Solution Manual, which is an incredible resource for you guys. Okay, so last thing, I just want to finish off. There's a very short section, 9.6 we're going to skip. We're going to, we just have not been doing comparison of the differences between two binomial proportions. We've been doing comparisons for means, of two means of continuous measurements, but we have not been doing comparisons of two binomial proportions. That's just something we've had to leave out of the course to make room for other stuff. It's not that hard, but it's just not a topic that we're covering, so don't bother studying it. I've taken it. It's not on the list of sections that we're covering, so just don't waste your time on that. Certainly you can go back and read about it. It's interesting enough and useful stuff, but it's not going to be on the final exam. 9.7 is very short. And so let's just quickly walk through 9.7 and then we're finished chapter 9. So 9.7 is called some comments on hypothesis testing. There's, and one more thing, sorry, I'm jumping around a little bit. I'll come back to 9.7, but one more thing about comments on hypothesis testing. One other thing that the textbook makes a big deal of, and I don't think it's such a big deal, but I just feel bound to comment a little bit about it, is this idea of significance. Just when we talk about statistical significance, and that just means that p value is less than, 5%. Okay, so that's statistical significance. So that's, we say something is statistically significant, meaning that there's a low probability that it's false or a high probability that it's true. That is statistical significance. And the textbook tries to draw a distinction, or it correctly draws a distinction between that and significance in everyday language, everyday language usage. So when we say something is significant in every day, I mean, that means it might have a big impact on us, say economically or health-wise or whatever. That's what we mean by significant in ordinary language. That's not at all what statistical significance means. Statistical significance is really a kind of a technical term, and it's about something that we should pay attention to. It's probably true, it's likely that it's true, but that doesn't mean that it's important. So that's one comment about significance, and that comes from 9.5, but it's connected to this 9.7. So 9.7, just review what it has to say here. There's two kinds of errors. Remember that we can make a type 1 error. The probability of a type 1 error is alpha. There's also this type 2 error, beta, and really you should be quoting your betas as well when you write stuff, but that's something that we've been dodging in this course, and because it's very hard for us to calculate by hand beta, so I'm just going to forget beta. But if you're going to do statistics professionally, you certainly need to know about beta as well. So beta, if we know beta, then we can use less weaselly language. We can say exactly what we obtained and exactly the various probabilities that we've made an error. But if we don't know beta, then the kind of weasel words that we're going to use and that I have been using are that the data do not support the rejection of H sub 0. Okay, so this is instead of accepting accept the null hypothesis. And accept is used because it's a single word, it's kind of pithy and it's easy for us to communicate. But when we write it's easy for us to communicate to other professionals if we say we're accepting the null hypothesis. But if we're communicating to the general public, then what we should say as more weaselly words, the data do not support the rejection of H sub 0. So instead of accepting the null hypothesis, we'll say the data do not support the rejection of H sub 0, of the null hypothesis. And then instead of just saying the words null hypothesis, which is guaranteed to frighten any person who hasn't taken a statistics course, expand what the null hypothesis is when you make a conclusion. Data do not support, evidence does not support. Okay, those are evidence. Okay, so those are kind of ways of expressing it. And really what this says isn't that H sub 0 is true. It says it's probably true, but we should investigate more. So more investigation may be warranted. Particularly if our p-values are close to 5%. If they're way off, like 20%, I've had these p-values in my own research. Sometimes you get p-values of 20%, 60%. So there's nothing there if your p-value is that high. But if your p-value is like 6%, and you think maybe there's still something there. Just that I didn't have the power to resolve it. I didn't have the sample size, so we may want to increase n. Right, so that's what really we're saying here when we say the data or the evidence do not support the rejection of the null hypothesis. We're saying that we need to really study this a little more. We're going to increase n the next time we study this, and maybe we'll start to see more precise results, and in that case, we may be able to give a clearer picture. All right, so that is one thing in 9.7. And the other one is some words that we use, and I sort of outlined this earlier, but let's go through it one more time in more detail. So the p-value is greater than 0.05, then we say it's NS, not significant. And that is with the caveat about the meaning of the word significant. It's not statistically significant. So not it's just something we don't bother putting that word statistically in. Maybe we should, but okay. So the p-value is less than 5%, but it's greater than 1%. We say it's significant. And if you like, you can qualify that at the 5% level. And if the p-value is less than 1%, highly significant. P-value is greater than 0.1%. We say highly significant. And finally, if the p-value is less than 0.1%, we say very highly significant. Okay, so really I think the p-value stands on its own. It says, anyone who knows a little bit of statistics can interpret the p-value, but for those who really don't understand statistics, then this terminology might help to get the message across. It's just that we also have to be clear that what we mean by significant isn't that it is significant as economically or in our lives or in our health or whatever, but it's significant statistically, meaning how sure we are that these results are true, how confident we are in our statements. So very highly significant means also that we're very confident that there's, say, a difference or that one thing is less than another or whatever. All right, so that is 9.7. That's the end of chapter 9 for us. So please now study up chapter 9, do the problem set, do the extra problems if you have time, and this material will be on our next quiz and will be on the final exam. This is the core of the course right there. We've done 8 and 9. That is the real core. Next, I'll give you a preview of what's coming up next. Chapter 10 is what do we do for small samples? And this is very useful to know. When we design experiments, we have control over the sample size, but sometimes we're provided with data that is a small sample. Can we still make conclusions with it? And the surprising answer is yes, under certain conditions we can. Do a lot, even with very small samples, like even an N of 10 or something like that. We have methods now that are fairly recent, developed in the early 20th century compared to some of the other methods that are more recent compared to the other methods, I mean, that are actually powerful enough to help us do inference for small samples. So that is useful, particularly in biology. So if you take a biology course or something related to biology, like kinesiology or whatever, you often end up having to deal with small samples. Am I going to go out and fish to catch 30 fish so I can do my statistics, or am I going to catch 5 fish, 10 fish? Well, I'm lucky if I catch one fish, but I hope you understand what I'm saying here, that it's much easier to do small samples, much less expensive. So this is going to be important for us, particularly if you're interested in biology. They use the small sample all the time. So that's what's coming up next. Chapter 11 is comparing more than two populations. That again happens in tests that we design. So you may have more than one treatment. So you have a treatment like a pesticide that you put on, but usually you can test multiple pesticides all at once. So you might have 3 different kinds of pesticide. So you can design an experiment that compares all 3 against one another. That's what Chapter 11 is going to be about. Chapter 12, I'm thinking we might end up skipping it. There's just a little tiny chunk of Chapter 12 that we need. Let's see how it goes. I think we're going to drop Chapter 12, but all that we need there is the bivariate statistics. It's revisiting the bivariate statistics with hypothesis testing. So it kind of fills in the gap, a little weakness that we had when we did bivariate statistics in Chapter 3. We're just making it more rigorous and using the framework of hypothesis testing for bivariate statistics. If we have time, we'll get into that. I'm beginning to wonder. Anyway, Chapter 10 is pretty short. 11, I'm going to skip all the nasty parts, so it'll be pretty short too. So we may have time for 12. I'll see what we can do. All right, so that's it for the rest of the course. So thank you for listening in this long, and please do try those problems and be ready for the quiz that's coming up next Thursday. All right, talk